Is it cooking? It's cooking. There we go. Free, well here, we'll do this. Free food, sand volleyball. Volleyball. I'm an expert at sand volleyball. Oh yeah. I bet you he'd be somebody you want on your team. Yeah. just chill at the net. Seriously. You probably have to be careful about like ceiling fans.
Yeah.
Like,
the worst is my room, like at my house back in Illinois. It's like a small room, so I'm getting dressed and I put my arm through my shirt. I'll hit my elbow on the fan every so often.
Where in Illinois?
Malkina.
That sounds made up.
That's not Native American from Montreal.
Okay, so but where is it? Like a Chicago suburb?
It's like between Chicago and Joliet.
Okay.
A little closer to Joliet.
I'm from Champaign area. So I'm downstate. I'm the better part of Illinois.
You're from Illinois. I'm from Chicago.
Yeah.
Two different states.
Right now, Illinois is like 72 degrees, and Chicago is like 8 degrees warmer than here. So it's crap. Okay, free food, sand volleyball. Anything else? Raffle prizes. Any good raffle prizes, or we just keep it a generic?
I don't know. That's up to Val.
So no, probably not. It's like whistles. you have a 1 in 40 chance of winning a whistle. We don't. That would be cool if we had yo-yos. We should get computer science yo-yos.
That would be the ones that light up like when you go down and sense something.
I remember when they used to have like the Dunkin' yo-yo commercials, and they made them look cool. Like they had all sorts of different Dunkin' yo-yos for doing different tricks and stuff. Now it's like yo-yos aren't cool anymore.
I have a yo-yo.
Yeah, you're tall.
That's an accurate statement.
That's there. You're tall. Okay, so sand volleyball, raffle prizes, skeet shooting.
What did you say?
Skeet shooting. Anything else?
The Facebook group says fellowship.
I can't put that on the slide. Is there a purpose for it? Is it a celebration or is it a recruitment?
No, I mean just like the end of the year cap off.
So, but now you're out of here after this year, right? So this is like free food and you're out the door. Yeah. So you cut all ties. Yeah, makes sense. So going away party. BYOB. But yeah, bring your own Bible, exactly. Whatever you got on this quiz, we'll add 2 points for the joke. Okay, so I'd encourage all of you to come to that. In fact, let me put this on my calendar so I show up.
Funny, a couple days ago at track practice, one of the discus throwers is an art major. I was just kind of like, if that whole thing doesn't work out, you could just be like a skeet shooter. Just pull him or throw it.
Regents Atrium. You said something about skeet shooting and other stupid stuff? 4:30. What's this? All right, got it. I'll be there, especially for the skeet shooting. Well, yeah, I have to supervise the grill. I'm a taster. I do that every week at church. I sell script at church, so it's like gift cards, but the church gets like a cut. So I duck out like during right before the last hymn, and so I go into our fellowship hall room thing where like they do coffee hour. They have food and stuff. Like each week somebody does. So I have to sample everything before the crowds get there. Quality assurance, exactly. Plus, then I steal soda out of the fridge. So I don't have to drink. Yeah, and I tell the pastor. I'm sitting there drinking. I said I stole another soda. All right. So free food. Is there going to be drinks as well? Free food and booze. Well, no. If you do an E at the end, then it's anti-dry campus. Booze, it's like, who knows what's going on. All right. So questions about that. Everybody should go to that thing. Another announcement. Senior seminar presentations. These are next. So Tuesday is at 5:03 from 2:35 p.m. till 6:45 p.m. Thursday, 5:05. And then, what's the other one? Is it Wednesday or is it a Tuesday? Tuesday the 10th. 5:10 from 3:10 p.m. until 5 p.m. These two are in Pharmacy 008. All right. So, oh no, this one's not. This one's an S120. So obviously these span a long time. You should be getting a email from CUW All or something like that today with the PDF that, and I'll put it up on Slack as well, but the PDF that lists all the different senior presentations and what the topics are and stuff like that. If you show up to at least 2 presentations, that's a 1-hour commitment. I'll give you a free quiz. I'll encourage you to come to more than that so that A, you're supporting the seniors, B, you're seeing kind of what's in store for you later on, so on and so forth. But especially when we're in the pharmacy room, you know, we want to try to fill that the best we can. Typically you get crickets. You have these students that have prepared all semester with this big presentation and stuff like that, and then nobody shows up. So, huh?
Where are those first two for the pharmacy?
It's the first floor of pharmacy, the giant lecture hall dealy thing.
Which person named that?
Who?
Yeah, who are the first two?
Who are the first? No. Each there's a bunch of people. Oh, I get you. So each presentation is a half hour.
Okay.
Yeah. So the PDF that'll come around, and like I said, I'll put it up on Slack as well. Lists for each day, who's presenting at what time slot, so you can pick and choose when you want to come. You don't have to come and sit there this entire time. You can if you want. I'd encourage you to do that.
I feel like we did get email about that.
Yeah. Huh?
We did get email about that.
Yeah, I sent one out. There's been a couple of changes to the order of who's presenting, but there'll be a new one coming out today. That's pretty much what you already got. But you can read the description of each topic. So I encourage you to come to the ones, regardless of the quiz, the free quiz dealie. I encourage you to come to the ones that are of interest to you, and maybe stay for the ones that are at least seem tolerable to you. But it should be, we have, I think, like 24 or 5 presentations, I think. So it's going to be a long haul. Technically, there's another one Friday morning. I think this is Friday, what is that, 5/13? Friday the 13th. Appropriately so. This is Ryan Guy. His presentation. He's been in Korea all semester.
Is it senior SEM or is it just a presentation on Korea?
No, senior SEM. This is his senior SEM presentation.
So is he working on it over there right now?
Well, yeah, he's over there and he's supposed to be working on it.
I haven't been keeping up with the vlog.
Is he coming back or is he like videoing?
He's coming back. He'll be here that day. So that's at the end of the week at this is 10 a.m. Okay, questions about any of that? All right, so let's go on to merge sort. So the homework assignment for yesterday was to, for today is to write merge sort. I got you started with an initial call to merge sort produces a call to our merge sort helper, which goes ahead and fills in the blanks for the initial begin and end. That guy. All right, and then here's what merge sort helper does: is it goes through, and as long as begin is not equal to end, as long as we're not dealing with a one list, which is already sorted, we'll call merge sort on the left, we'll call merge sort on the right, and then we'll do our merge step. All right, so the homework assignment was to effectively fill in the blanks here and write this. How did that go? Was it as easy as bubble? No, not as easy as bubble sort. Okay. When I put up a post, so it looks like the bubble sort from Wikipedia is actually the bubble sort I taught. Wikipedia calls insertion sort, and the bubble sort on Wikipedia is kind of like this weird swap thing. So if you did that for your homework assignment, that's fine. What I showed you last class, I've historically called bubble sort, and it kind of makes sense. Things bubble to the top. So, but whatever, they're all order n squared, cheapo ones. So related to the quiz here, what is big O notation, and what does it pertain to? Why is it important-ish? Go ahead.
It talks about the effectiveness of sorting algorithms.
Okay, so really the effectiveness of any algorithm, but we've talked about it in the context of sorting. And why might it be important? What does it actually pertain to? When I say something has a big O of n squared, what's that actually talking about? Go ahead.
Isn't it like the amount of steps that it's for run-throughs?
Yeah, I like to think of it as number of comparisons. So it's not officially the number of if statements, but I like to think of it as the number of comparisons. It kind of parallels that. So things that have a higher order have more comparisons, and more comparisons equals more technical CPU time. You got to ask a question that takes time, right? All right, so let's think about merge sort. For starters, an important aspect here is this idea of being able to keep track of begin and end. Okay, so we have to generically come up with an algorithm for calculating the begin and end of our sublists, right? So we're going to start off by writing a piece that shows us how this guy is dividing up, but we need to initially figure out how do we split begin and end. All right, so if this is begin and this is end, so 0 to 4, we've decided that our middle might be here at bucket 2. How did we calculate that? So if we want to figure out begin 1, end 1, begin 2, end 2, what is begin 1 equal to? It's equal to begin. What is end 2 equal to? End. Okay, those are the easy ones, right? What is end 1 equal to? We need to have a generic algorithm that calculates the end value, the halfway point is really what I'm talking about. How do you generically discover the halfway point? So end minus b divided by 2?
Yeah, and plus begin.
So end minus b divided by 2 like that?
And plus begin.
Plus begin?
Yes.
Okay. Okay. So if we have this sublist here, well, and then what's B2 before we go on any further? This is E1 plus 1. 1 ahead of it. Okay. So this is the important magic, right? Okay. So if this is our begin and end minus begin, 4 minus 0 is 4. Divided by 2 is 2. Plus 0 is 2. That's our middle point. Fair enough. Okay. What if this was end? 2 minus 0 is 2. Divided by 2 is 1. Plus 0 is 1. Seems to work fine. We could have come up with a much simpler version of end, or end 1, if we only ever were worried about the left half. It's the right half where things get weird. So let's assume that I'm dealing with that sublist, let's say. It would actually be this sublist, but let's just do the math here. So this would be 4 minus 2, which is 2, divided by 2, which is 1, plus 2, which is 3. All right, so that's where we get our middle point. Make sense? All right. So we're happy with these little math formulas for figuring out our left half and right half. Okay. So here we'll actually steal these guys. So if begin is not equal to end, we need to go ahead and calculate our left and right. Left and right halves, I guess. Actually, you know what? There we go. All right, so begin 1, end 1, begin 2, end 2. Oh, thank you. All right, then we need to call merge sort on the left. So we'll call merge sort helper, passing it the same array, passing it begin 1, end 1. Let's do this. Then we call merge sort on the right, passing it begin 2, end 2. All right, then we need to do our actual merge step, right? So merge step says we need to create a temporary array that is, and keep in mind that eventually these guys are going to split up to the point where begin and end are equal, and then we bounce back up. All right, now we need to merge those guys together. So we need to create a temporary array big enough to hold all the elements from the portion of the array we're currently looking at. So if I'm looking at this, let's say that guy right now, the begin and end that looks like that. So if I'm looking at this portion of the array, how many, well, I know it's going to be 2. How do I get 2 buckets out of that? How do I calculate that I need a temporary array of size 2 if I know that begin is 3 and end is 4? Is it end minus begin plus 1? Is that the size of our temporary array? Okay. So I'll need a temporary array. This guy's going to be index 0, 1 of size end minus begin plus 1. So int array temp is equal to a new int array end minus begin plus 1. That's the number of elements that are going to be in that array. Okay, but understand that temp is indexed at bucket 0. All right, now I need to keep track of the beginning of my first, so this is my first half of my list, this is my second half of my list. So I need to keep track of the beginning of each of them. I happen to already have pointers, begin 1, begin 2, that point to the beginning of those guys, right? So when is begin 1 legal? As long as it's less than or equal to end 1. When is begin 2 legal? As long as it's less than or equal to end 2. Okay. So we know we're going to have to go through this many times and place stuff, right? We've calculated a temporary array that is the perfect size for the number of questions we have to ask and the number of things we need to place. So we'll go ahead and say for int I is equal to 0, I is less than temp, I plus plus. So each time through, temp.length, each time through we're going to be placing an element at position I inside of temp. And the element we're going to pick is the next smallest. Okay, that makes sense? So we're going to ask our disqualifying questions first. We know if we are inside this loop, we have some number to place. Okay? So we can ask an initial question if begin 1 is greater than end 1. If that's a true statement, then we know we're off the end of our first list. Therefore, we're just going to take the answer of our second list. So we'll go ahead, and what we're going to do is we're going to modify B1 and B2. We're going to keep incrementing those guys to take us through the list. So we're kind of hijacking those variables. So if B1 is greater than E1, that means that the left half of our list has already been exhausted. We've already placed all those values. So we'll go ahead and say temp at bucket I is equal to AR at bucket B2, whatever B2 currently is, because we potentially have been modifying it. Okay? If you want to make that, let's actually just make that less, let's make it more explicit. We'll call this left pause, we'll start off at B1, right pause, we'll start off at B2. So what we're really asking is left pause greater than E1? If it is, go ahead and grab the value from right pause. Else if right pause is greater than E2, if the right position is an illegal position, if it's off the end of that portion of the list, we'll say temp at bucket I is equal to AR at bucket left pause. Now in either one of those cases, when we select a winner, we need to make sure that we increment right pause. Now we've learned about this stuff. We could technically do that, and that would work, right? Because the plus plus says, give me the current value of right pause and then increment it. But what I've taught you is don't risk it. It's guaranteed that that would work, what I just had there. But rather than having to remember how the plus plus works, we'll just go ahead and say right pause plus plus on its own line here. Nobody's impressed if we save one line of code. So when we place right pause, we increment right pause. Place left pause, we increment left pause. Else, if we're sitting in here, that means that we have two accurate, two legal positions that we actually have to compare. All right, so we'll say if AR at bucket left pause is less than AR at position right pause, then left pause is our winner. So we're going to do that stuff. Else right pause must be the winner. So we'll do this stuff. Make sense? So it's a bunch of questions. So if we're out of stuff on the left, take the thing from the right. If we're out of stuff on the right, take the thing from the left. If we still have stuff on both sides, let's compare them. If left is the smaller one, we'll grab the guy from the left, increment. Otherwise, the right one must be the smaller one, or at least it's equal to. And we'll grab the one on the right. If it's equal to, it didn't matter who we declared to be the winner. All right, and this is going to happen temp.length number of times. So when this is done, one thing you maybe haven't noticed, but notice when I put the cursor right next to this curly brace, it highlights the matching one. So sometimes that's helpful, so especially in this case where we have so many curly braces. So when we know right here, temp is filled up with our values in order. We need to now copy those back into AR in place. We have to replace the positions of AR with the contents of temp. Temp is indexed from 0 to temp.length minus 1. AR is indexed from begin 1, well, from begin to end, from B to E, right? Those are the buckets in there. So we're going to go ahead and say int pause is equal to 0. That's going to be the guy we use for temp. In fact, let's call it temp pause. We'll be explicit. Temp pause. All right. So we're going to be placing bucket temp pause from temp into a position in AR. So we'll say int I is equal to B. I is less than or equal to E. I plus plus. So this will take I on a voyage through the specific indexes in AR that we're interested in. So we'll go ahead and say AR at bucket I will get the value of temp at bucket temp pause. And then we need to make sure we do temp pause plus plus. So this will copy the contents of temp back into the appropriate location inside of AR. Make sense? So we've done our sorting, we did our merge step, we put the numbers back into AR, and now we can end a natural death. All right, so at the end here, we don't have to do anything else special. We don't have anything to return because we've sorted our portion of AR in place. That make sense? So merge sort says if it's an unsorted list by definition, that is, it's not a one list, call merge sort on the left, call merge sort on the right, which might turn into more left and right calls to merge sort. But when our version finally returns, we know we're dealing with a sorted left half and a sorted right half. It might be a one list, it might be a 20 list. We don't know, okay? Because we have several copies of merge sort helper kind of flying around at the same time. But this particular guy's perspective, when we're sitting right here, we have a sorted left half and a sorted right half. That's all we know for sure. Make sense? And then what are we going to do? We're going to merge those two sorted halves together, producing a sorted list between B and E, and letting either the next guy up know about it, or maybe we were the original call and we're done. All right, questions about that? So with that in mind, we should be able to fill our array, print it out, call merge sort on those numbers. Merge sort's going to then pass that array on, filling in the blanks for bucket 0 is begin, and ar.length minus 1 is end. Merge sort helper should then go and do its thing. Split, call merge sort on the left, call merge sort on the right, merge over and over and over and over again until finally it's array, sorted and merged all the individual pieces of that array. So when this guy finally returns after potentially several recursive calls, we should have array of numbers sorted. Make sense? Now, when we look at this, we might say that this is more complicated than what I advertise as bubble sort, which Wikipedia calls insertion sort. Call it whatever you want, it doesn't matter. Okay? It's a sorting algorithm. Is this one more complicated? Really, the scariest part here, we used several lines just to calculate 4 numbers. There's nothing horrible about that. This guy was a pretty important portion of this code, right? Making sure we got that one math problem right. If we fail there, all else is out the window. Let's just look at that. If I take the plus B off there, bad stuff. So it's a very important number we get right, calculating the middle point. Doesn't even have to be the absolute middle, to be honest. Just has to be consistent. And we can't leave any buckets behind. Okay? So this is our way of making that consistently true. These 2 calls to merge sort are actually very simple calls, but this is probably the portion of merge sort that makes merge sort difficult to understand. Whenever we deal with recursion, we're kind of putting one copy of this function on hold and waiting. These are almost promises. So this guy blocks. So while this guy's working, we never get to the second call. So our original 2 calls to merge sort, this call gets called first, blocking the other guy, which then calls 2 other times, which then calls 2 other times, which then calls 2 other times, so on and so forth. So we have all these like promises for merge sort to have finished its job, but those guys are not working simultaneously. That makes sense? Let me ask you this. Is there a great reason why we couldn't call merge sort on the left and merge sort on the right at the same time? Are they relative to each other? I mean, can't we sort the left half and sort the right half simultaneously? They're not reliant on each other, are they? All right, so, but when I make a recursive call, I'm not doing them at the same time. I'm focusing entirely on the left half, and then focusing entirely on the left half of that, and then focusing entirely on the left half of that, before I ever even start paying attention to the right half. Now, if we have a multi-core CPU, so even our budget pleaser computers today are at least dual core, right? So your computer can actually do 2 things at once. Why shouldn't we sort the left at the same time as we sort the right? That is to say, make these guys non-blocking calls. Now, this is actually a really big concept in computer science even today. We have this, let me introduce a couple of terms here, and then we'll talk about it in terms of kind of this old school thing, merge sort. The real question I was just thinking, do I give extra credit for attending the Grace cookout? Might be worth it. I mean, this is Emily's going away party.
Yeah.
Where are you moving and stuff? What's the story? A job somewhere? What's?
Johnson Controls, I'm gonna do this associate project manager.
Okay, so you're not moving anywhere. So you could probably still come up here and do Grace stuff next year.
Yeah.
But you're just not going to.
Yeah,
But you're not going to. I get it.
She's never
It's dedication.
She's never come back here again.
This is done. Just done. Yeah. I compliment your dedication. But this is the first year of Grace, and it did really well, didn't it? I mean, we've tried to start up an ACM computer science group here, like a traditional one, several times, and it's just flopped. And and typically in computer science, women's groups don't fly that well. It's just, you look at your classes, you have a very small population of females compared to males. It's just the nature of technology courses. I don't know why, but it is what it is. So the fact that, you've had an average attendance of many people, that's way better than, because the guys are lazy and they throw chunks of metal around and they're just idiots. Huh? What? Just grunts. That's right.
Last year, one of the meetings, this guy, he threw disc and yelled at it to go further, and the wind did just right, it picked up at that exact moment. Come on, go.
Do they still do javelin?
Yeah. One of the freshmen here is actually the one guy at our conference.
Isn't that javelin seems dangerous?
Yeah. Well,
That's spear throwing, right?
Yeah. They were all ancient, fighting styles, throw shotlets and hammers at people.
That doesn't seem like a Christian approach. Let's get down out there in the field and throw some spears. All right. So we want to talk about communication. So we have synchronous, and we have asynchronous. Okay, this Keynote's not complaining. Okay, so these are 2 different communication styles. Synchronous communication is known as blocking communication. Asynchronous is non-blocking communication. So when we make a synchronous call, i.e. our recursive calls, historically they wouldn't have called those synchronous, they just would have called them blocking. Synchronous really comes into play when we start talking about communicating over the internet. That's when they kind of started using synchronous and asynchronous type communication. And really, this comes down to this guy runs in what's called a background thread. So it runs inside of a new thread, so it can happen seemingly at the same time without blocking new things. And this guy runs in the main thread. Those are probably two truths, and we're going to talk about threads here this last week of class. All right, so synchronous versus asynchronous, blocking versus non-blocking communication. So the question here is this. Let's get back to here. If these were asynchronous calls, if somehow this call to merge sort ran inside of its own thread, that is, it did not prevent us from moving on to this guy and going ahead and sorting the right half. It ran inside of its own thread or something. It didn't block for some reason. Would that be a benefit to us right now, as this code's currently written? We've said at the high level that there's no reason why we can't sort the left and the right half simultaneously. But why would that actually become a problem here? We're relying on something right here, right?
Wouldn't it go too fast?
Potentially, right? Potentially. We're going to spawn off a thread, a worker bee, a child process to go and sort the left half. We're going to spawn off a worker bee to go sort the right half. And then we're going to get dumped out right here because neither of these lines block. We don't have to wait for this guy to complete. We don't have to wait for this guy to complete. So now we're sitting right here in our code, yet we kind of make the assumption that they've completed. We're going to start merging stuff that might not be ready to be merged. That make sense? Because the left half and the right half might still be busy. Okay, that's like me sending you to the grocery store to get something, me sending him to the grocery store to get something. I'm going to start cooking. Okay, but I don't have the stuff to cook with yet because hasn't arrived because you guys are slow, right? So that's the deal here, and this actually becomes an interesting problem in computer science today. That is to say that the modern approach to everything is asynchronous. Make non-blocking calls. Why do you think that is? Why do you think asynchronous communication is preferred in modern application development? I kind of mentioned that these terms are usually used when we talk about grabbing things over the internet, things like that. Why do you think it's go ahead?
Is it faster?
Okay, tell me what you mean by faster. But we just talked about one problem here, that sometimes fast isn't better. What's the nature of our applications today? When you think about software, you download an app, whether it's for your computer or your phone, whatever. What's the nature of those? Usually there's a graphical user interface, right? And you're typing stuff in, you're clicking buttons, and you expect things to happen. Okay? When you hit a button on your phone, you don't want it to pause. You don't want it to feel like, oh, did I miss the button, right? You want it to do something, right? So that means non-blocking. You don't want your application to feel like it stalls all the time or that it's real jumpy because it's having to do communication in the background. And so, like if you're using the weather app or something like that, and you type in your zip code, or it determines with location services what your current location is in the world, and it goes and gets that information. The app doesn't just freeze, right? What does it do? It goes to the next page and usually shows a whole bunch of those little pinwheel things as stuff is loading. Right? So you get some sort of feedback that stuff is happening in my app. That make sense? Okay, so that's why asynchronous has become cool. Right? Now, we can pretty easily make our app asynchronous here. We're going to talk next time about creating threads. Okay? But if we do that, how do we prevent us from moving on here? I mean, it's great if we go ahead and we make this non-blocking and make this non-blocking, especially with the truth that we have multiple cores in our machines. So this computer has a quad-core processor in it. So I can technically do 4 things at once. And then each of those things are individually scheduled. We talk about all that stuff inside the operating systems course, 350. But so we might as well take advantage of that horsepower to sort different things. But now we need to have some mechanism right here for making sure we don't move on and try to merge until we're prepared to merge. Does that make sense? All right. So for next class, we're going to have another quiz. Okay. This is based only on what you know now. I want you to come up with a, this is equivalent to our ghetto sort. So a ghetto solution to waiting here until both sides have been sorted if the calls above did not block. That make sense? So come up with some solution based on what you know now on how we can, I promise you it won't be a good solution, but it might be a solution that works. But I want to think through that idea of how do you handle non-blocking communication. All right, I will see everybody on Monday.